quantum computers on the cloud. So these are physical cloud or some other cloud? Emanuele?
I think we should ask the previous speaker to stop the sharing so that we can that I can share my screen.
Absolutely. Satyabrit, can you please stop sharing? Your screen is being. Now,
okay, cool.
There you go.
Nice. So let me see. Okay, so I share my screen. Yeah, it looks. So these are, real clouds with water inside.
Absolutely.
H2O.
Looking forward. Okay, please. The stage is yours.
So thanks a lot. So I understand you have had a long day with a lot of lectures, many interesting lectures actually. So I would like to really thank Surin and also Prasanta for the invitation and to schedule such a wonderful event with so many lectures, and they are also recorded so that people can come back to them. I see many interesting topics or related to different aspects of quantum technologies. So what I would like to tell you today is about some recent work that we've been doing in the field of quantum simulations using quantum computers, and I will start with some introduction. But first of all, because this is a Zoom meeting, let me tell you where I am. So I guess, at least from the names, most of the attendants are from India, probably from Kolkata, I guess. So this is, well, it's a zoomed in map of Israel. As you know, it's a relatively small country. And I'm affiliated with Bar-Ilan University, which is located in the suburbs of Tel Aviv. As you may know, the main cities in Israel are Tel Aviv and Jerusalem. They're actually only like, I don't know, 50 kilometers away. So, you know, it's a small country. But we have a nice campus. Surin, have you ever visited Bar-Ilan?
Oh, God.
No, you haven't? Not yet.
I'm unable to unmute. Can you hear me?
Yes, we can hear you.
Yes, I did once. Yes.
Okay, great. So I hope you find it nice. So this is my group, my research group. We deal with the dynamics of complex quantum systems. So it's a theory group. Here I will mention some works that have been done in collaboration with Eran as well, and Surin and his student. And I would like also to mention a collaboration with Otano Rajak, who spent a couple of years as a postdoctorate fellow in Bar-Ilan University, and he is now a professor at the Presidency University in Kolkata. Although I won't really mention the work that we did together because it's just a different topic, but I felt it was relevant. So for these works on quantum computers, we have been very lucky to collaborate with people that actually build those quantum computers, because as a theory group, we don't have those capabilities. And in particular, during the previous year, I spent a sabbatical in the group of Matthew Rigor at a company called Rigetti. They are a leading company in building a full stack quantum computer using superconducting circuits. So I enjoyed a lot spending time with them, and I will mention some of the collaborations of the works we did together in this presentation. Okay, and we are funded by the Israel Science Foundation. Okay, that's it for the just generic introduction. And now let me tell you about quantum simulations. So I'm not sure if I looked at the list of speakers. I didn't recognize anyone speaking specifically on quantum simulations. So that's why I put at this slide. Maybe, you know, the concepts, you are probably familiar with them, but I think it's important to, you know, understand what we are doing. So essentially the idea is, imagine that you have a complex molecule or a complex material that has some quantum properties that you would like to analyze. For instance, I don't know, this could be transport fructafrine or you know, any other quantum property of a material. And the idea is that because this is a quantum problem, it's a very complicated one. And in practice, if you want to even start analyzing this problem, so let's think of the simplest configuration in which you have, say, n atoms. On each atom, there is just a single site that could be either occupied or unoccupied, so like a spin or a 0, 0, 1 situation. Then you have the Hilbert space is 2 to the n, and what that means in practice is that if you want to describe the state of this material, you would need a vector with 2 to the n numbers. So it's a huge vector. And that's due to the fact that the state of the quantum system is a superposition of all possible states. So unlike in the classical case, if this was just a classical situation, then you would just need one number of size 2 to the n. So actually you would need just n digits, n zeros and 1. That's okay. It's a relatively small number, easy to store and easy to work with. But for a quantum computer, because you can be in a superposition, you actually need the prefactors of those 2 to the n. So you need a vector that is a huge vector with all these numbers together. Okay, so that's quite obvious. And the question is how you solve it. So the way as theoreticians, we would like to solve it is using maybe some equations, say write down the Schrödinger equation that describes the motion of the electrons in this material. The problem is that these are very complicated equations with so many variables, an exponential number of variables. And so they are very hard to solve. What we do usually is that we apply some approximations. And for instance, in the case where n is very large, we can maybe do some approximation, maybe describe it as a field theory. So there are all sorts of analytical methods to deal with those systems, which have achieved a lot of success in describing, for instance, universal properties of material, classification of different type of materials, but they have their own limitation. In particular, it's hard to say for a specific configuration what is going to be the property of the material. So say a question like, I give you a material, is it a superconductor? Okay, it looks like a very simple question. I mean, is it a normal metal or is it a superconductor? Actually, it's very hard. So going from the specific to the microscopic model to actually a prediction, it's something that is very hard to do analytically. So another way that people have tried to solve this problem is to use classical supercomputers, as we are all now familiar with big data, artificial intelligence. They are capable of solving really extremely large problems with billion of, or sometimes even trillion of operations or parameters. So these are huge numbers. The problem is that this 2 to the n is really bad and the reason is, as you all know, 2 to the 10 is about 1,000, which means that 2 to the 20 is about 1,000,000 and 2 to the 30 is about already billion. So it means that when I give a system of say 50 qubits, you will have, it's already, much more than the storage than the entire computer in the world could store. So you cannot treat this problem even on these extremely powerful computers. So, and that point was actually made even, a long time ago in the beginning of the 80s by Richard Feynman. He has this famous article on quantum computers where he says, if I try my best to make equations look as near as possible to what would be imitable by a classical probabilistic computer, I get into trouble. So if I try to describe a quantum system using a classical description, like a probabilistic classical description, this is what he calls a classical probabilistic computer, I get into trouble. And that's exactly this exponential increase of the number of variables. That's the trouble that he gets into. And then he came and suggests an idea to how to deal with this problem, which is that if we can't solve the problem using a classical computer, maybe what we should do is actually to use another quantum system. Why? Because the quantum system is also following the same laws of nature, the same superposition laws of nature, and therefore it's more suitable to solve a quantum problem. And that's really the idea of a quantum simulation. It's something that has been done very successfully using many different platforms. And in particular, I think one field that has been really driving this idea of quantum simulation is the field of ultra-cold atoms, where they use laser fields to trap atoms inside the lattice, say inside the periodic lattice, and then they think of these atoms as electrons. So you have an entire atom that is cooled down to extremely low temperature using laser cooling, and then it behaves as a quantum entity, which mimics the behavior of an electron in a material. So this is already quite mature field, one that I also worked with in the past. And what I would like to propose in this talk And of course, many more researchers around the world are also driving the same direction. So it's of course a community effort. Is the idea that maybe we can also use quantum computers for the same purpose. So we can use a quantum computer to simulate, to mimic, to describe other quantum systems. And in particular, I would like to discuss today the use of quantum computers on the cloud. So before going into the cloud part, let's focus on the quantum computer themselves. I'm sure quantum computers have been mentioned before in the conference. I just want to say here very quickly that there are many different platforms, and each platform has its own advantages and disadvantages. And I would say that right now, the two major platforms that are being used are either superconducting circuits or trapped ions. Superconducting circuits are more scalable because you use lithography, so it's relatively easy to make many of them. The problem is that they are quite noisy. We will mention the effect of noise quite extensively during this talk. Trapped ions are much less noisier, they have less noise, but it's very hard to trap many ions. So actually, I will tell you what are the numbers, but it's hard. It's not really scalable. And also another problem that people don't often mention, but for me, I think it's quite relevant, is the fact that they're also quite slow, meaning that applying a gate on these ions requires you some time, maybe just some fraction of millisecond. But if you need to make many operations, that could become a problem. These are the two leading platforms. There are others like read-bar atoms. So these are neutral atoms that are trapped. You see here this Super Mario. So I can't see your faces. I don't know how young you are, but I hope you can all recognize this Super Mario, beautiful, beautiful, beautiful movie by the group of QERA, a spin-off of Harvard, led by the Misha Lukin. What you're seeing here, okay, it's just a game, but you really, if you freeze on one of these pictures, it's really a picture in which you see individual pixels that are individual atoms. So what they're capable is to take single atoms one by one with a technique called optical tweezers, place them in an array, which is completely configurable. And well, okay, if they repeat it, they can make a movie. But it's quite remarkable that they really have single atom control of many atoms, not just a single atom, but many atoms, hundreds of atoms that they can place at will. Another platform that is currently very considered is the platform based on photons, entangled photons, and the related concept of measurement-based quantum computers. So these quantum computers with photons work in a different way, which is, however, equivalent to the usual way. And the challenge is really to control these single photons and measure them, entangle them. And although there are several companies working on this, I would say they are not there yet. So has not been really demonstrated yet as a working quantum computer, although the scalability is built in. So it is true that when they will be able to just build a few, because photons are so easy to create, it will be easy to scale up to large numbers. So that's an advantage of this technology. And another technology that people are considering, more sort of condensed matter inspired, these quantum wells that are generated by two-dimensional 2DEG, that Surin, you certainly know well. And the idea is, okay, if you can control a two-level system, well, you can now call it, instead of a spin, you call it a qubit, and then you make a quantum computer. Here, the reaching very, very high fidelities is extremely hard due to the technical difficulties. So some demonstrations are existing, but I don't know, it's still a bit lagging behind. However, in reality, I've taken this list from a friend of mine who wrote a nice review on quantum computing. Actually, right now there are almost 30 different technologies or platforms that have been proposed to build quantum computers. And the feeling is that if quantum computers are going to have some impact, it's probably going to be maybe through some surprise, maybe some of these ideas that at the moment maybe can create only a single or a couple of qubits will have some explosion, some new advance, etc. So it's not clear yet how we are going to build the ultimate quantum computer. But it's important to understand that there are different platforms and the differences between the different platforms. Okay, so that's in general quantum computer. What is quantum computer on the cloud? Well, the idea is simple, is that there is someone who builds a quantum computer, but it needs also users, right? If you're a company, you need to show that, well, people use my quantum computer. And the way to do that, of course, is through the internet. And there is right now a whole network of providers that allow you to connect to many different quantum computers. I think the leading one, at least from my perspective, and again, this is only a partial list, are IBM, Amazon, and Microsoft. Actually, Amazon and Microsoft don't have their own quantum computers yet, but they allow you to connect to many different quantum computers. So this is, again, a partial list of the quantum computers that you can connect to. Some of them are neutral atoms, trapped ions, superconducting circuits. So you have all sorts of, and the idea is that there will be some sort of language, maybe a universal language that you can use to program all these quantum computers in the same way that you can write a program in C and then run it on different classical computers. And I think actually the language by IBM, QIQT, is now seems to be like the leading, the most developed, I would say, language for quantum computing. And it has been adopted slowly also by other players. Okay, so let me give you an example. So let me see, let me try to do the following. I would like to see if people are listening, and also if you have ever tried the quantum computer. So I would like to ask you to maybe click on, is there some sort of like, or how do you do that? Maybe, yeah, you could put a like. Yes, I think if you go to more and then reactions, you could put a like or raise your hand if you have ever used the quantum computer on the cloud, maybe in particular through IBM or other platforms. So I would like you to raise your hand, or maybe put some reaction.
Emanuele, you want me to do it?
Well, no, you can like, well, you can make a like if you used it, but I don't know. I was like thinking to ask some feedback from the audience. I'm not sure exactly how to do that. At least in my case, there is a way to
somebody
raise a hand. Okay, we see one raising hand. Thanks, Tamoy. I appreciate that. So more people who use the quantum computer on the cloud, at least 2 of them. Great, thanks, Pratha. Okay, great. So I see at least someone is listening, and also you have some experience. So, but let me give you, for those who haven't used it. Okay, great. Some more people are raising their hands. It's great. Thanks. So let me show a very simple example that you can all realize using this IBM website. Let's assume you want to create this cat state. Okay, so the cat state is a state in which it's a superposition of 0 and 1, here with 3 qubits. It takes the name cat, like a Schrödinger cat that is alive and dead. And you can create it using a circuit. So this language of circuits assumes that there are 3 qubits. You apply Hadamard gate. So the Hadamard gate basically is just preparing a superposition of 0 and 1. That's for the first qubit. And then there are these entangling gates that will create an entangled state where all the qubits are either in 0 or in 1. So you can create this circuit and you can run it on a simulator, and you can, what you usually do, you prepare the state and measure it, and you will get like 50% 0, 0, 0 or 50% 1, 1, 1. That's what you expect to find. However, when you run it on the quantum computer, because of the noise, actually you get a slightly different result. So still, well, it's most probably either 0, 0, 0 or 1, 1, 1. But there is also some noise. Sometimes you get the wrong answer. So these quantum computers are noisy. Actually, this was an experiment already 2 years ago. So last year I said, okay, I want to, let's try now what happens now. And I retried. On the one hand, you see that the noise is lower, is much smaller. So there are smaller noise, so that the quantum computer improved. This is a new version of the quantum computer. But there is more imbalance between 0 and 1. Which is, so I don't know, there are good signs and bad signs. It's tricky. I mean, it's tricky to make a quantum computer with a large fidelity. So actually, how can we quantify these errors? I think when starting to think or planning to do anything with a quantum computer, I think it's a good idea to have some thought of what can I do with those quantum computers. This is a question I'm often asked. So when you enter into the details of the quantum computer, so that's a typical quantum computer by IBM, you would see many numbers. And there are these two numbers that I'm interested in, which is like 1% for average CNOT error. So it means at every time you apply a gate, there is a 1% error, plus the measurement, the readout has a 3% error. So is it a lot or a few? And my thumb rule, it's thumb rule, so it sort of works, gives you the idea. You think of how many gates you have, you multiply by 1%, then you make how many qubits you have, you multiply by 3%, and you can get until 50%. So that's my thumb rule. When you got to 50%, then that's it. The program won't work anymore. So that's sort of the limit. And then a question that you may ask is, let's say I want to make a square circuit. So I want to have n qubits and apply n gates on each qubit. So that will lead to approximately n square number of gates plus, so it's like n square plus 3n. And then you may ask, what is the largest n that I can apply? So certainly if n is 100, then there are these too much error. Actually, the largest number you can have is 5. So if you have 5, you see that you are already close to the 50% thumb rule, Dalla Torre's thumb rule. And indeed, I mean, people have called this number the quantum volume. Actually, for historical reasons, instead of calling the quantum volume 5, they say, oh, the quantum volume is 2 to the 5. So, well, whatever. Anyway, the quantum volume is defined, as you may guess, in a little bit more formal way, but the thumb rule I gave you is the right way to proceed. So you imagine a square circuit, and then you ask yourself how many gates I can apply before I get to the 50%. It gives you a rough estimate of the quantum volume. That's a typical quantum volume for superconducting circuits. Trapped ions actually have a larger quantum volume. And these are news from February 2023, so it's relatively new. There is a company, it's called Quantinum. They are a spin-off of Honeywell, and they have trapped ions. The error rates are much lower. So instead of 1%, you have 0.1%. And what they were able to do is to have 2 to the 15 quantum volume. So basically, this square circuit, they have like 15 qubits with 15 gates. So square circuit with 15 qubit with like 225 gates, which is quite remarkable. And that's actually the highest number that has been reached so far. And that sort of sets the limit of what can be done with the current technology. Okay, so they call it, well, the title was Quantum Volume Reaches 5 digits for the first time. 5 digits just because 2 to the 15 is 3 times. Okay, whatever. So what is the challenge of quantum computing as I try to explain right now? So the idea is the following. We have a lot of beautiful circuits, models, algorithms, Shor algorithm, Grover algorithm, all sorts of beautiful things you would like to do with a quantum computer. And then you have the reality. And the reality is that, well, actually I can use, I don't know, 5, 10 qubits. So you have a beautiful algorithm with 1,000 qubits. This is your dream, the theory. And then there is reality, which is like 10 qubits at most. So what would you do? How will we proceed? And I think there is really a gap here between people doing quantum information theory and people doing, building the hardware. And the hardware already has developed a lot. I mean, things, this 15, quantum volume 15 is something that was unimaginable even just a few years ago. So the field is progressing a lot and quickly, but still there is this gap to fill. And what I think is that what we should do, and I guess, my talk and also other talks are in this direction, is you need to go both ways. So you need to improve your hardware. You need to improve you reduce the number of errors, and even at some point implement what is known as quantum error correction, which means that you want to be able to actually correct those errors. And in fact, there is a threshold, there is a theorem that tells you that there is a threshold above which you are really able to correct errors. The idea is that to correct an error, you need a more complex circuit. So you start with a circuit, you say, oh, I want to correct an error. Good, you take a more complex circuit. That more complex circuit will have more errors. So it's not clear a priori that you can even correct them because you grow in size and actually you make it just messier and messier. And actually there is a threshold. So there is a threshold above which, if the error is below that threshold, then you increase the number of corrections, and then you really make it less and less noisy. So less noisy. So that can work in principle. So people have been working a lot in improving the hardware and even demonstrating some quantum principles of quantum error corrections. But I think there is also the other side of the coin, which is that theory people also need to improve their models. So for me as a physicist, it's natural to say, well, if your hardware, if your model, if your physics doesn't follow the theory, then you should probably improve your theory. Okay, and that's what we do. And in fact, we have been quite successfully in using this strategy to suggest many different experiments that use small number of qubits. So that's the first, trick is if you use few qubits, maybe 5 to 6 qubits, then the errors is not too much, and you can still do something that is reasonable. And what I like about those papers that we published in the last couple of years is that actually in each of them there is some theory part, but also a small experiment. So a small experiment on a quantum computer that demonstrates the principle that we are going to demonstrate. And in particular, there is this very recent paper that we wrote with Soren, in which we speak about quantum error detection. So that's, I would say, the first step toward correcting an error is being able to actually recognize that there is an error. I want to really speak about this work. Soren knows it better than me, but the idea is that you can create a special state. It's called the cluster state, which allows you to detect an error. So when you measure, you prepare a state, you wait for some time, and then you make some measurements, and by making the measurements, you can know exactly which error has occurred. And so we tested it both in theory and in the experiment using the IBM quantum computers. So it worked nicely, I think. Okay, so for this talk, I didn't know a priori how much time I have. So I actually prepared 3 different topics. I'm sure I won't be able to talk about all of them. I'll probably actually talk only about the first one. And then if you're interested, you can invite me again and I'll speak about the other ones. So also in consideration of the time, in India is even later than here.
So the invitation is on.
Sorry.
So the invitation is on.
The invitation is on. Okay, great. Thanks, Soren. Okay, so no local games with 6 qubits. That's the first project I would like to tell you. I think it's nice because it's related to a game. It's pretty intuitive. So actually, there is a movie that Microsoft prepared on their quantum hardware, their quantum systems, and they invited me also to say a few words. So I'm going to show you a movie. Let me see. I need to share my volume. How do I do it? Let me see, advanced sharing option. Let me see. Okay, let me try to new share sound. Screen 2. Okay. Running a quantum program. Did you hear the volume? The movie?
Yes,
yes, okay, fast. Great.
Yes, a bit.
Yep. Okay. Well, we'll try. Anyway, the images are, yeah, okay. Let's see. No, where is it? Running a quantum program on a real quantum computer using Azure Quantum is magic. It's amazing.
Azure Quantum enabled us to create a first-of-its-kind course in which students analyze how real quantum computers perform. It was a unique opportunity to combine learning with doing in quantum information. After completing a series of team-based projects, students were able to design their own research problems and run experiments on the IonQ machine, accessed through Azure Quantum. These students had previously studied quantum computing in theory, but this was their first chance to program and evaluate real quantum devices. It was an incredible experience for them.
We used Quantinuum hardware accessed through Azure Quantum for testing the quantumness of the computer and comparing it with classical computers. We've challenged the computers to solve a certain puzzle. The classical computer had a success rate of 87%. But by taking advantage of non-local effects, the success rate of the quantum computer was a striking 97%. This game essentially proves that the quantum computer is quantum. The Azure Quantum Credits program has given us the opportunity to be the pioneers of this type of research.
Our project was an academic research collaboration between the Technical University of Denmark and KPMG. It involved neural networks, which are computer systems that mimic the human brain. By accessing hardware through Azure Quantum, we use quantum computing to train and control neural networks. People and organizations, they are beginning to realize the extreme power that lies in quantum computing. This is something that we can truly harness.
The word is out. Quantum computing is going to change how we solve problems.
Okay, so I hope you like the movie. And let me tell you, what are those numbers, these 87, 97? So let me try to explain you these concepts. So the project we dealt with was about non-local quantum games, which is essentially an extension of Bell inequalities with many qubits. I guess you all know what a Bell inequality is. That's a demonstration of the quantum, one of the most famous demonstrations of quantum effects, in which you prepare two entangled qubits, two entangled photons, for instance, and perform different measurements, and then demonstrate that these correlations are not classical. They are beyond classical. They are quantum correlations. And that's also related to the Nobel Prize of last year. So the Bell inequality, the usual Bell inequality is for 2 qubits. And the question is, how can you realize something similar with more than 2 qubits? So with many qubits. And this is essentially the idea of a non-local quantum game. Here, what we implemented is what we call the triangle game that was introduced by Brave, Gosset, and Koenig in Science, and then sort of extended and also explained a little bit clearer way by Daniel Miaka in PRL 2021. So what is the idea? This is a collaborative game, meaning that there are some players that try to work together in order to succeed in a task. And the quantum game, in principle, should be able to perform the task with a 100% success rate, while classical computers are limited to these 7-8. And okay, so what is the game? So the simplest realization has 3 players, and each player has 2 qubits. Okay, and there is a dealer, which is so each of the players needs to basically give out 2 numbers, 2 zeros and 1. 0, 1 here, 0, 1 here. That's for the first player, second player, third player. And they need to satisfy some rules. And the dealer checks whether all the players satisfied together the rules. As I mentioned, it's a collaborative game. What is the problem? The problem is that actually the rules change. So every time that they play a game, at the beginning of the game, they toss a coin. And the rules depend on the result of the coin. So here you see, because there are 3 coins, there are 8 possibilities, and each of the possibilities give rise to different rules. So the problem is, right now, the players are playing, they don't know what are the rules of the game. And the rules are built in such a way that there is no way to satisfy all the rules together. There is no strategy classical strategy that will allow them to win with 100% probability. In fact, without dwelling into the details, there is actually a very simple strategy that will allow them to win 7/8. So if they just write 0 everywhere, they always give 0, whatever, they always give 0, that will allow them to win all the rules except the first one. And so that's basically, that's it. So that's the best they could do. The best they could do is win 7 out of 8. How do quantum players improve on that result? The idea is that before tossing the coin, so after they toss the coin, they are not allowed to communicate. Otherwise, it would be simple that you would just tell each other what are the results of the coin. But before starting the game, what they do, they share an entangled state, actually a cluster state. That's actually the same cluster state that I mentioned before in work by Surin. It's a very simple state that can be created using a very shallow circuit. You see, I have here only 6 2-qubit gates. So it's a very shallow circuit that has a small error probability. So few gates. And then, so that comes before tossing the coin. Then they toss the coin and they measure. And here comes the trick. So the trick is that they will measure their qubit, the first qubit, they will measure it according to the result of the coin. So if the coin gives you head, then you measure X. If the coin gives you a tail, then you will measure Y. And then, as you know, the measurement that is performed on one qubit will affect the result of the measurement on the other qubit. So while this non-local effect cannot transfer information, okay, that's the famous paradox of quantum information. How comes that you can transfer information faster than the speed of light? Because when I measure here, I immediately have some effect on another side. The answer is you cannot transfer information. So the other players will not know what was measured by the player one. However, there is some correlation that is built, some special correlation between the result. So although player two will still see 50% 0, 1, so with the same probabilities, the probabilities are unchanged, the correlation, there will be built some correlations between the measure of player one and the measure of player two. That's the no-local effect that Einstein didn't like, and he called it this spooky action at a distance, but which is a property of quantum mechanics. And that's what is used by these players, by these quantum players, to achieve a better fidelity. So what we also added to this protocol was a small error mitigation. That's a simple standard error mitigation technique. The only thing that we did, which was sort of non-trivial, we said, well, we do error mitigation, but without letting the players. So the error mitigation is a classical post-processing of the results, which is aimed to cancel the noise. But we said we do not allow the players to talk together. So we mitigate each of the results of the player individually, and we cannot allow them to transfer information between them. Otherwise, we would be cheating. And that's what we did. Okay, so let me show you now these experimental results. So what I'm going to show you now are some error bars, so an histogram, which is the percentage of the success probability for different hardware. And there are two lines. One line is the random line. So if you just randomly write 0 or 1, it turns out you will still win with 3 eighths, which is 37.5%. While if you are a classical computer, you can win at most 7/8. So 7/8 is 87.8%. So this is this red line. I don't know if you want to call this quantum advantage. Maybe it's better to call it quantum violation. So, but if you have a result that is above this line, you know that it's a quantum system. It's not. It cannot be a classical system. So we performed this calculation using several quantum computers available on the cloud already a couple of years ago. And the result was not very encouraging because none of the computer was able to beat this threshold. However, after we posted this work online, actually we were contacted by people from Honeywell, and they said, oh, we really like your paper. Maybe there is a Honeywell H0, but there is also Honeywell H1, which works a little bit better. So we would like to test your program on the H1. We said, of course, do that. And when they did that, wow, okay, it worked. They crossed the line and they got 97%. So strictly speaking, it's not quantum computer on the cloud because they did it for us. But okay, we sent, well, it was on the cloud because we sent the program by email. So maybe it's still on the cloud. Anyway, so the idea is that, yes, this quantum computer can win this triangle game more than a classical game on classical players. And what I would like to say is that this is really a way to benchmark quantum computers. And so what we say is that H1 is much better than H0. And this is something that many other tests that have been performed on the same quantum computer also realized. So I think that it's really, what is useful is benchmarking the quantum computer using different algorithms so that you can compare different methods. And I think all the methods sort of agree that, let's say, Boblingen is much better than Melbourne, and IonQ is about the same as IBM Boblingen. So the different benchmarking methods seem to sort of match together. Okay, so this is why it was interesting from an experimental perspective. From a theoretical perspective, I think this project actually rose a theoretical question, which is does this mean that IonQ is not a quantum computer because it didn't violate didn't cross the line? So this is actually not true. So if I cross the line, that I'm sure that is a violation, it's a quantum computer. If I didn't cross the line, well, I don't know. So then the question is, what could you do? Can you do better than that? And the idea is that, being a teacher, I know that when all the students fail a test, what you would do is usually lower the bar. At least, I don't know, at least this is what we do in Israel. I'm not sure in India if this is the same. But anyway, from just the idea was to think about another test that will be easier to cross, another violation that will be easier to cross. And it turned out that this question was actually asked, and people used the language of cluster of the cluster state. So these are called stabilizer operators. It turns out that this cluster state is not just any state. It's a state that has many. It's I would say like an integrable state. So it's a state that has many local operators that are eigen for which this quantum state is an eigenstate. So when you apply this operator, this ZXZ operator on the cluster state, you get 1. So the cluster state is an eigenstate of all these SI. And actually so it's uniquely defined as the state. There is only one state that is an eigenstate of all these operators. And so you can use these cluster states to actually build many different tests. In effect, these rules that I told you about were really generated using products of these operators, of these ZXZ. So let's say if you multiply ZXZ, you multiply 2 ZXZ, you basically ZX, XZ. So you can multiply these operators and get the rules. And more in general, one could say, well, what is the most generic operator that I can build? Is going to be an operator that is going to be like the sum of all stabilizers, maybe also the sum of all the products of stabilizers, and so on and so forth. So overall, you will get a sum of 2 to the n stabilizers. So you get an operator, and you may ask, so this operator, you know immediately that it's also an eigenstate. The cluster state is an eigenstate of this operator, because the operator is just, so it's very easy to compute what is the expectation value of this operator in a quantum system. It is actually just 2 to the n. But then the question is, if I have a classical system, so a classical player, what would be the best solution for the classical game? And actually, it turns out that this is a non-solved problem. So we know how to do it numerically for small cluster states, not more in general. And it turns out that for the cluster state, it's 28. So which means that for 6 qubits, the best quantum game would get 64, and the best classical player would give 28. And one may also ask, what is the best game that they can play? What is the game for which the ratio between the classical players and the quantum player is the largest? And this was actually a question that had been asked some time ago by Cabell and co-authors. And they found that there is some operator, which is a sum of products of stabilizers. For that particular operator, the classical players get at most 19, and the quantum players get at most 15. So that's what comes out of this calculation. And these numbers, 19 and 15 for me are still a puzzle. So what I like about this project, that really raises interesting theoretical questions of, let's say, if I tell you n equals to 10, no one knows what are those numbers. What is the best quantum to classical ratio? So anyway, a perfect quantum computer will get 55. How about a real quantum computers? Of course, it won't get 55. Like in the previous case, we didn't get 100%. We'll get lower numbers. So for instance, in the IonQs, we got 41. And the point is that this 41, however, is still much larger than 19. So 41, the real quantum computer, doesn't work as well as the perfect quantum computer, but still it works much better than the classical computer. So we can engineer another game, if you want. We can think of another game that gives the best advantage to quantum computers, and make even a quantum computer that was not able to win the triangle game win this other game. Okay. So that was about the first project. I see we are almost out of time. So let me really quickly rush over these other two projects. Maybe I'm going to really just mention what the projects are about, and then there are some references that you can read more. So the second project that I wanted to tell you about is about simulating a Bose-Einstein condensate. So as you all know, Bose-Einstein condensation is a particular phase of matter. It's sometimes called the fifth phase of matter, and it's related to the world of superfluids and also superconductors. So it's a state in which the atoms, bosonic atoms, have long-range coherence. And what we did was to build a protocol that we realize an analog of that state using spins. So instead of using the bosons of the Bose-Einstein condensate, we created something that you could think of like a condensate of spin excitations. Then we probed it on both theoretically and on the quantum computer. So actually, this was a very small, condensate. It was a condensate of maybe 4 qubits. The 5th qubit was used as an ancilla for measurements. But in principle, the protocol is scalable. So if you give me a better quantum computer, or maybe an quantum error corrected quantum computer, then I can create a Bose-Einstein condensate with arbitrary dimension. And it was also a way to understand a little bit the difference between different types of Bose-Einstein condensate. You know that you can create a Bose-Einstein condensate of atoms, of bosonic atoms, but also photons. And then the question is, what is the difference between, say, a Bose-Einstein condensate of atoms and a Bose-Einstein condensate of photons? And what is also the difference between a Bose-Einstein condensate of photons and a laser, which is also a state of photons with coherence? Is it the same or not? And these are questions that we sort of dealt with as using the quantum computer as a motivation for our study. The other project that I wanted to tell you about is about encoding a quantum state. So imagine that you are given an interesting quantum state, and you want to create it using gates. It turns out that, in fact, recreating a generic state requires an exponential number of gates. So the depth, if you want to generate a generic state using gates, you will actually need very deep circuits. So the errors is really a true problem. And what we ask is, what if I have a target state that I want to create, and I cannot really create it? I want just to create an approximate state, and a state that has some overlap with the target state, not the state itself. So an approximate encoding. What is the best way to create it? So we develop a method that will find for you what is the best way to create such a circuit for a generic classical state, actually in particular for matrix product states. So these states that are used in quantum information theory. Okay, so that's what I wanted to tell you. Let me now basically skip to two additional things I wanted to tell you. So I wanted to tell you, something about startups, because in addition to my work at Bar-Ilan University, I'm also helping establishing a small startup in Israel. So I wanted to tell you that in Israel, there are quite a few startups now that are working in the field of quantum technologies and quantum computers at different stages. So some of them are really small, and some of them are already larger, like quantum machines that already has a product that they are selling. Some are more hardware or software-like. Again, this is just, and there are also more startups that some are also sort of secret, so I haven't really mentioned them yet. And here is Quantimize. So Quantimize is actually the company I'm establishing with my colleagues. We are, well, actually our funding is 0. So on the logarithmic state, it would be on minus infinity. But anyway, yes. And then I'm not sure if you saw in the news, but the former Prime Minister, Naftali Bennett, actually got into quantum technologies. He has some startup background, and he became the board. He was introducing the board of Quantum Source, a quantum technology. Bennett said, quantum computing is one of the few technologies that has the potential to move the world forward in a significant way. So he really likes quantum computer, and we like people who like quantum computer. We like Naftali Bennett, although no one, well, he retired from politics because, well, people now have other preferences. Anyway, so this is Quantimize, our our startup, what we try to do is to use quantum computers for combinatorial optimization. So that's a field where quantum computers are expected to have some impact, hopefully in the near term. And we are trying to do so. If you have ideas related to quantum information, and in particular quantum optimization, talk to me. And the really last slide is about, this is a personal initiative. It's called the Smart Archive. So the idea is that you want to be updated about the latest papers in the archive, but you don't want to get flooded by the number of new papers every day. So what you can do, you can go to this website, tiny.cc Smart Archive, and from there you can sign up for a free email. Every day you get a free email with just a few papers that are selected only specifically for you using a proprietary AI algorithm. And it's for free, so you should really try it if you haven't. And you get all these preprints per day, and then it will, it's very easy. So basically, it uses your previous papers. So if you don't have any paper online, it doesn't work as well. Well, it doesn't work at all, actually. So it uses your previous paper, assuming that you're probably still working on related topics, and then it selects for you what he thinks they are the best, or she thinks are the best papers for you. And we send you an email every day, and it works. I'm using it, and yeah, that's it. So thank you for your attention.
Thank you very much for this fantastic talk. Really enjoyed it. Now the session is open for questions. No questions? How can that be?
Yeah, probably people are ready for dinner already.
No, not really.
Can I ask a question?
Oh yeah, absolutely. Go ahead.
Yes. Thank you for your talk. In one of your slides, you informed that noise becomes less. My question is, what kind of actions were applied or improvements introduced to reduce the noise?
Okay, so this is, so it's a really harder question. And there are all sorts of questions, or all sorts of errors, and they depend also on the technology. So for instance, if you think about superconducting circuits, one of the main challenges is fabrication. You need to fabricate these superconducting devices. By now, the humanity is extremely well in doing anything with silicon, right? We know how to create silicon that is very, very clean and have lithography, this electron beam lithography that goes down to the nanometers. It's fabulous. It took the humanity a lot of time and actually also a lot of money to reach that level. Unfortunately, silicon is not a superconductor. Well, luckily for the semiconductor people, but unluckily for us. So you need to use other materials where the techniques of fabrication are not as well developed. So you have imperfections. You have there is an effect called two-level systems. So these are tiny impurities that are in your material, and they can fluctuate. And they also behave as a quantum qubit, and which is coupled to your quantum computer. So your quantum computer now has your 20 qubits that you control, but in addition you also have some spurious additional qubits that are coupled to them. You don't know what they do. And sometimes it turns out that when they cool down the superconductors to very low temperatures, they need to warm it up. When they cool them down, they behave differently because of these two-level systems, because the two-level systems now are in a different configuration. So I think fabrication is a huge challenge, and again, a lot of success has been achieved. But still there are errors. Another problem is the control. So the control requires microwave pulses that needs to be very precise and also very, I would say, focused in a sense. So one of the problems is that you need to, you want to control a single qubit, not all the others. But the problem is that, microwave, the wavelength is centimeters. So very simply, it's very hard to focus a microwave. So you cannot really focus. So what you do, you use qubits that have slightly different frequencies. so that you can address each qubit individually because they are narrow enough so that there is almost no overlap. But this almost no overlap may be some finite overlap. Then there is the problem of coupling the qubits together, and that also gives rise to noise. So the main challenge is not the single qubit gates. The single qubit gates actually can do them with very good fidelities. The problem is the two qubit gates, the one that couple the qubits. How can you couple qubits in a controllable way? So the way that is usually done is that there is always a small coupling between the qubits, and then you essentially parametrically enhance this coupling. That's essentially the way. But which means that you need to, to excite those qubits, to excite those systems, to drive those systems, if you want, to parametrically enhance the coupling between the qubits, and this leads to noise, etc. So there are many challenges. Then there is the measurement. This is another problem. This is for superconducting circuits. For trapped ions, my understanding is that the problem is more about trapping the ions, so keeping them still, trapping many of them, and also coupling them. The way they couple them, which is quite amazing, is they actually use the motional degree of freedom. So when the ions are trapped, they have some interaction between them and they form like a lattice. And you can think of this lattice as having some phonons that are that they are the collective motion of the ions. So these phonons essentially couple the ions together. So by selecting the right phonon or a like superposition of phonons, you can actually couple selectively one ion to the other. But it's hard if you have many ions because there are many phonons and you get stuck. So the way they do it, they actually move these ions, which is quite remarkable, while still having the quantum information on. They physically take an ion, move it to some region where they can interact all the ions together, and then move them away, and etc. So you really need to physically move the ions in space, and that takes some time. And again, maybe the time is just a millisecond, but if you need to make many operations and to repeat it many times, it's a lot of time. So there are many technological challenges, and unfortunately, as a theoretician, I cannot really help. I mean, what we more do is, okay, what can we do with a noisy quantum computer? And we can get some input. Sometimes we can try to benchmark what is the error. We can say, oh, there is maybe different type of errors, and we can say this is the one that is more dangerous to us. Yeah, hope this answers this question.
Okay. Any other questions? You can unmute yourself and ask. I don't see anybody else unmuting. I have a small question. Emanuele, you had this list of 3 papers which you discussed. The second one was about a BEC. I'm just curious, with the 4 spins, you could see a reasonable BEC, but now if you have 2 BECs, will you see some kind of Josephson effect, oscillations? Is it possible to simulate? I'm very curious. I cannot help asking.
Well, I mean, I think simple forms of Josephson oscillation, you can probably see them. The question is, well, if you want to have, let's say, 2 condensate, you would need to have at least 4 ions. So you need to have more. So I would say the answer is yes. I mean, all these effects, that after all, these are just 2-level systems. So everything you can see in a quantum system, you can also simulate on the quantum computer. But really the challenging is having something whose signal is not killed by the noise. So the question that one we need to ask is, so in theory, sure, I can see anything, but then will I see that in practice, which may also be related to the connectivity. That's also something I didn't touch upon, but it's a very strong limitation, in particular superconducting circuits, where each qubit is not coupled to all the other qubits, but just to the neighboring one. And so that limits, the way that qubits can interact. And so but that's not a problem for us.
So 8 will be a problem at 8. You need 10, which means, right? 1 ancilla plus 4 and another ancilla plus 4.
Let me tell you that in reality, to really make a BEC with 4 qubits, we actually needed 2 ancillas. But when we tried it on the Rigetti hardware, I'm not sure. I'm not sure if this is really recorded or just Well, anyway, the Rigetti hardware is quite noisy, so it was hard to see. Even using 2 ancillas, it was a challenge. But they are improving as other companies are improving. So maybe I think before going to 8 qubits, I would like to see 2 ancillas with 4 qubits. That would already be, which is really a true BEC, because the ancillas is what we do. Basically, we want to measure the number of atoms to mimic the BEC. The idea of a BEC is that in a BEC of molecules, of atoms, you have in total a well-defined total number of atoms. So the idea was to measure the total number, post-select the one that has the right number of total number of atoms. So what you need is the log of the number of atoms. And for 4, you would need 2 ancillas. But then again, you need to couple all the qubits to the ancillas. So in principle, we know how to do it in a scalable way, that it grows only linearly in the number of qubits, but still it was, yeah.
Okay, I understand. Okay, thank you. If there are no more questions, last chance. If there are any questions, you may unmute and ask. Okay, looks like no. Okay, Emanuele, thanks a lot for your talk. It was very, very interesting. And also all the very best for your startup.
Yeah, thanks.
And see you next month in Israel.
Yeah, absolutely. Absolutely. See you, Sorin. Thanks.
Yeah, see you then. Bye-bye.
Yeah.